Hey everybody, Mr. A here. Today I'm going to be walking through the Unit 1A study guide with you. I'm going to be going over every single question, giving you all the logic, all the formulas, all the processes that are required to solve these problems and be as prepared as you possibly can be for our Unit 1A summative. Question 1 asks us to name the plane represented by the bottom of the box. All right, for visual sake here, the bottom of the box, we're looking at this portion right here that I'm outlining in red. As it says in the direction, that contains points F, K, G, H, and E. Very important note down here, really what this is assessing is this fact that the points that you use to name a plane cannot be collinear points, right? So we're gonna use 3 points to name any plane, right? They just cannot be on the same line. So that means for this group of points that we have here, F, K, G, H, and E, the only combination of those that doesn't work is F, K, G, because F, K, and G are collinear points. So literally any other combination using 3 of these letters would be an appropriate name for this plane. An example of that could be F, K, H would be an appropriate name for the plane. Question 2 has a bunch of parts to it. There's actually a question up here though that first asks us to name the intersection of the 2 planes with appropriate notations. So one thing students are easy to forget is the intersection of planes. Anytime planes intersect, they intersect in lines. Okay, so for the figure shown here, that would be this line right here where our planes kind of slice through each other. And to name that line, I would just use any 2 points that are on it. So I have points A, L, and B to choose from. A simple name for that line would be line AB as the intersection of our 2 planes. All right, moving down our list here, we have to name 4 points. Remember, points are just dots in geometry. We have a whole bunch to choose from. An example that could work for this answer, I'm just gonna do the first 4 points that I see. Point K, point E, point D, point C, right? Lines, remember we identify lines by having 2 arrows at the ends of them, right? So this right here is not a line because it only has 1 arrow. So that makes these 2 are lines right here that I've highlighted in red. I just need to name those with points. Okay, for this one here, I can call that line AB. Make sure you get our symbols correct on here. For our other line right here, again, I can just use any 2 points that are on it. I'll call that one line HG as an appropriate answer. All right, name 3 rays. Now at first glance, this one might be a little difficult because the only obvious ray is that one, all right? But remember, there are rays that can be part of lines, which I'll show you in a second. Let's name the ray that I have highlighted here first. Remember, rays have to be named in very specific ways. The end point must be the first letter in the name of the ray. So this ray must start with the letter C. From there, I can put any other point on the ray as a name for it. So I can absolutely call that ray CD, okay? But rays are also parts of lines. For an example, right here is a ray. Starting at L and going past B forever, that can be called ray LB, right? There's also a ray right here that starts at F and passes H forever. I could call that ray FH. So remember, rays can be part of lines. Our next part here says name 3 collinear points. Remember, collinear just means on the same line. So points A, L, and B are all collinear points. Another acceptable answer for that would be H, G, and F. Those are all collinear points. So are C, D, and E. Those are collinear, right? Name 3 coplanar points. So coplanar things are just things in the same plane. If we look at C, D, and E, they're all here on this blue plane, that vertical plane right there. Those are all coplanar points, C, D, and E. Another acceptable answer would have been H, G, and F. Those are all on this smaller plane down here. Those are coplanar points. It says give 2 names for the plane shaded in blue. That's this tall one right here. And remember our rule, to name planes we use 3 points and they cannot be on the same line. So I cannot call this plane CDE. Right, so I'm gonna have to use K, or even I can involve A, L, and B because those are technically on this plane as well. So an appropriate name here could be CDK. Be a good name for this plane. All right, another good name I can say like ABE. Those are all points that are on that blue plane. And there are several other examples that would be appropriate to name that plane. says name 3 line segments. Again, at first glance, there are no segments because remember, segments don't have arrows at the end of them. They're just straight. But remember that segments can be parts of lines. They can be part of array. For example, there's a part right here from just E to D. That's segment ED. There's a part right here from L to B. That's segment LB. There's a part right here from H to G. That's segment HG. And there's several other correct examples for line segments in this figure. Question 3 is asking us to draw and label some geometric figures, starting with this. Obviously, we need to know our symbols. That's one arrow, that is a ray. So we have a ray DE. Rays will look like this. One arrow on one side and endpoint on the other side. But the key here in this is making sure that we put these points in the right places, because remember that rays can only be named in one way. That first letter has to be the endpoint. So this has to be point D over here. This can be point E, that's a ray DE. Our second thing here has 2 arrows, that would make it a line. And if it's called line FG, that just means on our line needs to be a point F and a point G. They can be anywhere on that line though. Our last thing has no arrows above it. That is the symbol for a segment. So we need no arrows, but endpoints instead, right? And then our name for that would be our endpoint. So H and I would go on either end, and it doesn't matter which end they go on, as long as they're on the outside. That'd be segment HI. Question 4 asks us to write the segment addition postulate for this figure. So ignore numbers for a moment. Remember, the segment addition postulate is just adding together all the little parts to create a larger segment. So in this example, we have this little part, AC. So my postulate would start with AC. That would be added to this next little part, CD. That would be added to our next little part, DB. And when I combine all of those together, that gives me the entire segment from end to end, which is segment AB. So that is the segment addition postulate for this example, right? Next, it says solve for AC if AB is 15 units long. So we already know CD is 4, DB is 3. They're telling me now that the whole thing is 15 and asking us to solve for AC. I'm going to put a variable there because there's no variable already involved. I can call that X. And now I can substitute these values into the segment addition postulate to solve for that missing piece. So AC is X. CD is 4, DB is 3, the whole thing AB is 15, and we can do the appropriate algebra here to solve for that missing piece. 4 plus 3 is 7. When I subtract 7 from both sides, I get 8 for that missing portion for segment AC. Question 5 tells us that L, M, and K are collinear and that M is between L and K. Let's make sure that we can draw that. Remember, collinear means on the same line. It says M is between, so I can just put that somewhere in the middle here, between L and K. So M is between, it's in the middle, L and K are at the other ends, so this would be the figure described in this question. We're told that LM is 21, we could put that in our figure. We're told that LK is 30, so the whole thing is 30. And we're being asked to solve for MK. Right here, this missing piece on that segment, right? Remember, we can set up an equation using the segment addition postulate. So the little piece where our 21 comes from, that's the LM. If we combine that with the other part, MK, that gives us the entire segment LK. And from here, we can substitute our values in to have a solvable equation. LM is 21, MK is X, LK is 30. Now we can subtract both sides by 21 to get our missing measurement, that MK is 9 units long. Question 6, just like question 5, it's worded a little bit different, but it's just going to end up being the segment addition postulate again, just with more algebra involved. So we're told F is between G and R on a segment. So again, we can draw that. F is between, so it's somewhere in the middle, and then we have G and R on our segment. We know that GF is 3x plus 11, so I can put that there. We know FR is 5x minus 4, so that can go there. We know the whole thing, GR, is 12x minus 9. So this would be the figure that represents this problem. And again, the segment addition postulate would help us to solve for x in this scenario. So little piece GF on the left plus little piece FR on the right combine to give me the big piece, GR, the whole thing. With this, I can substitute in these values to get my correct equation. So GF is 3x plus 11, FR is 5x minus 4, GR is 12x minus 9, and then we're on our way with algebra. Here we would combine like terms first. So on the left, I have a 3x and a 5x. Those combine to give me 8x's. That positive 11 and negative 4 will combine to give me positive 7. The right side carries down. Now I need to move terms to get all my x's on the same side. So for this, I would subtract by 8x on both sides. Leaves me with 7 on the left. 4x minus 9 on the right. I'm going to move that over here. 7 equals 4x minus 9. To get that 4x alone on the right now, I can move the 9 to the other side by adding 9 to both sides. 4x carries down, the 9's cancel on the right, 7 plus 9 gives me 16. Divide both sides by 4 to get x equals 4. X equals 4. From there, it's asking me to solve for segment GR, all right? So GR is 12x minus 9, so I just need to plug my 4 into that. So 12 times x, which we just solved for, was 4, minus 9. 12 times 4 is 48. 48 minus 9 will give us 39 units for segment GR. Questions 7 and 8 involve using midpoints or finding midpoints. Question 7 asks us to find the midpoint of a segment. That would require us to use the midpoint formula. Please make sure that you're taking the time to label your points before you plug them into formulas. This is one of the most common errors that students make. They don't label, they input something incorrectly or put a wrong sign for something into their formula, and so they have it wrong from the beginning. Right, so take the time to label, it can save you from those mistakes. So our midpoint formula is x1 plus x2, so negative 15 plus x2, which is 19, that's over 2. That gives us our x coordinate. We do the same thing with our y's. y1 plus y2. I like to write things with the exact signs that my formulas have. So 8 plus negative 20 would be y1 plus y2. From there, we need to add on our numerators. So negative 15 plus 19 is 4. 8 plus negative 20 is negative 12. Then we are dividing, and I'll get 2 when I divide 4 by 2. So that's my x coordinate for my midpoint, and negative 12 divided by 2 gives me negative 6 for my y coordinate. That would be my midpoint in question 7. Question 8 also includes the word midpoint, but notice it tells us where the midpoint is located. And so this can be solved with the midpoint formula, and if you watched my 1.3 video there, I gave you an example of that. But I think there is a more logical approach to solving this, where I draw this vertical segment. Right, we have T and S as my endpoints for this segment. We know that because it says right here that it's called segment TS. I'll just call this midpoint M there in the middle. We know the midpoint's at negative 12, positive 1, so I'm just going to write that right here, negative 12, positive 1. We know the endpoint T is located at positive 19, negative 7. And what we're trying to do is figure out the pattern here of how we get from our starting point to the middle. Because if this is halfway in between, however far we travel here, we'll have to travel the same distance to get to the other end of the segment, all right? So starting from positive 19 to get to negative 12, we would subtract in order to do this, all right? And the number that we would subtract here would be 31. Now that may not be an obvious value for some people, all right? In order to find this value, what you can always do is find the difference, the change in these by subtracting them. If you take the number at the middle and you subtract it by the number at the endpoint, so negative 12 minus 19, that would give you negative 31. That is why we're subtracting by 31 to get from the end to the middle. So if we subtract by 31 to get to the middle, then subtracting by 31 again is going to get us to the opposite end of this point, which would be at negative 43. All right, the y is maybe a little bit easier for our number sense. To get from negative 7 to positive 1, I would be adding, and I would add 8 here. And again, if that number is not obvious, you can always take that number at the middle, 1, subtract it by the end number, negative 7, that gives you positive 8. So I'm adding 8. Adding 8 gets me to the middle. If I add 8 again, 1 plus 8 gets me to positive 9 for that missing endpoint in this problem. In question 9, we are finding the distance between 2 points. Hopefully those 3 words there are the signal for you that we're going to use the distance formula to do this. In order to use the distance formula, we want to label our points first. Remember that this prevents us from making mental errors. It allows us to accurately plug things into our formula. All right, from there we plug in. The distance formula is the square root of x2, so 0, minus x1, which is 7. That gets squared, and then added to the same thing with our y coordinates. So y2, negative 12, minus y1, which is negative 1. Again, we see that I like to plug things in with the exact signs that they have. I don't change anything mentally before I write it down. And from here we calculate. 0 minus negative 7 is negative 7. Right? Negative 12 minus negative 1 is negative 11. After we do parentheses, we would do our exponents. Negative 7 squared is positive 49. Negative 11 squared is positive 121. Those then get added together to give us the square root of 170. From here, we can always evaluate whether or not this is a whole number or a decimal. The square root of 170 is not a whole number, it's a decimal. So at this stage, I would just keep it as this exact answer of the square root of 170. Right? If you're not one of my students and your teacher has taught you how to simplify radicals, then by all means simplify for your answer. Right, question 10 is asking us to determine if segment AB is congruent to segment AC. Let's first make sure that we know that symbol means congruent. Let's also make sure that we know congruent means equal in measure. So we're really being asked if these 2 sides are the same length, right? And we find length on the coordinate plane with the distance formula. So we're going to be using that on both sides. To stay organized, I'm going to write the name of the side that I'm going to find first, AB. I'm going to write down the location of the points that are involved here, and then I'm going to label them and plug them into the distance formula. So x1, y1 for one of my points, x2, y2 for the other, and then we're off with our distance formula. Right, first parentheses is x2 minus x1, 1 minus negative 4. That gets squared, added to my second parentheses, y2 minus y1. It also gets squared. We're following order of operations, doing parentheses first. So 1 minus negative 4 gives me positive 5. 5 minus 1 gives me positive 4. Then we are squaring. We're doing our exponents next. So 5 squared is 25. 4 squared is 16. When we add 25 to 16, we get the square root of 41. Okay, I'm going to erase this just so that I have room to show my next distance formula on screen with the graph. So we just found out that AB is equal to the square root of 41. So if we get the same value for AC, then these segments would be congruent to each other. So now for AC, for A, I'm getting negative 4, positive 1. For C, I'm getting 0, negative 4. I just want to say really quick, remember the only reason I erased there is so that I could fit everything on screen. Obviously, when you're taking an assessment, don't erase any work that you did. You make sure you're showing all the work for your problems. So here are my points for A and C. I'm going to again label them x1, y1, x2, y2, and plug those into my distance formula. So x2, 0, minus x1, which is negative 4. In my first parentheses, that gets squared, add to my second parentheses, which is y2, minus y1. So negative 4 minus 1. Again, parentheses first. 0 minus negative 4 is positive 4. Negative 4 minus 1 is negative 5. Then we're squaring. 4 squared gives me 16. Negative 5 squared gives me positive 25. Helpful tip and reminder, when you square in the distance formula, you will always have positive values afterwards. You should never have anything negative and no subtraction going on at this step of your distance formula. 16 plus 25 gives us the square root of 41, which was the same as AB. So our answer to this question is yes, they are congruent to each other. They're both the square root of 41 units long. Questions 11 and 12 go over weighted average. Weighted average, remember, is just average. It's just adding stuff up and dividing by the total number of values. Just remember that the weights are our total values in these problems. So 11 has a weight of 7. That means there's 7 11s. But instead of writing 11 plus 11 plus 11 7 times, right, we can just write 11 times 7. right? 9 has a weight of 2, I can just write 9 times 2. 21 has a weight of 4, I can just write 21 times 4. So that's the adding all of our values together. And because this is average, we need to divide by the total number of values. And that would be the sum of all of our weights. So again, the 7s, the 2, and the 4. I'm adding those numbers in parentheses down here in my denominator. And then I'm just calculating. 11 times 7 is 77. 9 times 2 is 18. 21 times 4 is 84. 7 plus 2 plus 4 is 13. Grab a calculator really quick. 77 plus 18 plus 84 gives us 179. And when we divide 179 by 13, we get a decimal about 13.8 when we round to the nearest tenth. 12 is the same weighted average question, but dealing with fractions for our weights instead of whole numbers. Our setup is still the same though. We're taking our values and multiplying them by their weights. We're adding them up and then dividing by the total number of values or the total number of weights. So for this problem, I have 16 with a weight of 3/4, so I'm doing 16 times 3/4. That gets added to our next value, 28, with a weight of 1/4. And again, the denominator is the sum of these weights. So I get 3/4 plus 1/4. All right, from here we're calculating 16 times 3/4 would just be doing 16 times 3, then dividing by 4, which is a whole number, it's positive 12. 28 times 1/4 would just be 28 times 1 divided by 4, which is 7. All right, hopefully you caught that. I like multiplying by fractions by multiplying by the numerator and dividing by the denominator. So 16 times 3 and then divided by 4 gives you that 12. 28 times 1 divided by 4 gets you that 7. On the bottom, I have 3/4 plus 1/4. That would give me 4/4. Up top, 12 plus 7 is 19. 4 over 4 is just 1. Anything divided by 1 is equal to itself. The good thing here with these fraction weighted average questions is the fractions are always going to have a sum of 1. Our last two questions involve perimeter and area on the coordinate plane. Starting with question 13, we're going to have a triangle. We have 3 points. We need to graph those on our graph. -3, -4 would end up right here. +6, -4 would end up right here. And we have +1, +5 right here. These can get connected to create our triangle, like so. In order to help us identify sides here, I'm going to name these points. So I'm going to call this one point A, call this one up here point B, this one point C. I'm going to start by finding the perimeter, and I'm going to put a little P right here just to stay organized, saying that all the stuff I'm doing right here is to find the perimeter of this figure. Remember, for perimeter, some sides we'll be able to just count with our finger, like side AC. I can just count that. That is 1, 2, 3, 4, 5, 6, 7, 8, 9 units long. Right, 9 units. I don't have to show any kind of work or proof for that because it's countable. Right? For side A, B, and BC though, I'm gonna have to use the distance formula because those are diagonal. So remember, anything diagonal that you wanna know the length of, you're gonna have to use the distance formula on it. So I'm gonna stay organized. I'm gonna write AB, and I'm gonna write my locations down. A was at -3, -4. B is at 1, 5. I'm gonna label x1, y1, x2, y2, and I'm gonna plug those into my distance formula. Hopefully you're getting the hang of distance formula at this stage. x2 minus x1 would be 1 minus -3. That gets squared, then added to y2 minus y1. So 5 minus -4 gets squared. Order of operations tells us parentheses first. 1 minus -3 is +4. Guys, please use your calculators. Don't rely on mental math when you're adding and subtracting with negatives, right? 5 minus -4, excuse me, is +9. After parentheses, we're squaring. For 4 squared, I get 16. 9 squared, I get 81. Those get added together, and I get the square root of 97 for side AB. I'm gonna go ahead and write that up here so I can keep track of it. AB square root of 97. Again, when you're doing a quiz or a test, make sure you're keeping all work on the paper. I'm going to erase this just so that we can fit the rest of my work on screen. So that was side AB. Next is side BC. So again, staying organized. I'm saying, hey, here's my work for side BC. Point B, again, is at 1, 5. Point C is at positive 6, negative 4. Remember, the purpose of writing these down is so that we can label them and carefully plug them into our distance formulas. So D equals big ol' square root. We got x2 minus x1 squared. That's 6 minus 1 squared. Plus y2 minus y1. That's negative 4 minus 5 squared. 6 minus 1, parentheses first. 6 minus 1 gives us positive 5. Negative 4 minus 5 gives us negative 9. After parentheses, we square, doing our exponents. 5 squared is 25, negative 9 squared is 81. Those get added together. I get the square root of 106 for side BC. Again, I'm gonna stay organized up here. BC, the square root of 106. Right? From here, I have now the length of all three sides. I can calculate the perimeter of my figure. So AC 9 plus, now we have to be careful here. I'm not gonna write plus the square root of 97 plus the square root of 106 because those are not like terms. I wanna get them into like terms. Now, you could do these in your calculator, add them all up and round at the end. I'm just gonna take it one distance formula at a time. I realize that will give us slightly different answers with rounding in the end. Just wanna make sure that we're all on the same page here. So square root of 97, it's about 9.8. Plus the square root of 106, it's about 10.3. And when I combine all of those, 9 plus 9.8 plus 10.3, we get about 29.1 units for the perimeter of this triangle. So that's our perimeter part. Next, we need to find the area. This is a long problem here. However, the area in this problem is a pretty simple thing to do because what we need is countable. So remember, for a triangle, the area formula is base times height divided by 2. And for this triangle, I can use this bottom side as the base. Remember, we counted this side AC earlier. It was 9 units long. The height would then be something perpendicular to this side that measures to the opposite vertex, and that would be this line right here that I highlighted there in red. And again, that is just countable. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9 units long for my height. A helpful tip here is to remember that height is never diagonal, it's never crooked, it's always straight to the base, okay? 9 units as well for my height. And I can now calculate my area by doing that base of 9 times the height of 9 divided by 2. 9 times 9 is 81. 81 divided by 2 will give us 40.5 units squared for the area of the triangle. These problems will take a long time on the test. Make sure that we're prepared by knowing our formulas and knowing how to use the distance formula, knowing how to use our triangle formula. By the way, area of a triangle is not on the reference sheet for the test. All right, in our last example, we have to find the perimeter and area of a shape with vertices given 4 different points. Positive 5, negative 2 is right there. Positive 6, positive 1, right there. Negative 2, positive 2, right there. And negative 1, positive 5, right there. And that gives us this figure, this quadrilateral, this 4-sided shape. Some of you can tell right away this problem will take a very long time to do. We're going to start with the perimeter. Nothing countable on this side or on this shape. So we're going to have to do distance formula on all 4 sides in order to find our perimeter for here. I'm going to label my points A, B, C, and D, and we're going to get started. Right, side AB. Staying organized here. A is at negative 2, positive 2. B is at negative 1, positive 5. We label. Remember, the distance formula is going to tell me how long my sides are, which is what I need to know to get my perimeters, adding all the sides together. So, plugging in. x2 minus x1, -1 minus -2 gets squared, then added to y2 minus y1, that's 5 minus 2, gets squared. Parentheses first, -1 minus -2 is +1, 5 minus 2, +3. Now we're doing exponents, 1 squared is just 1, 3 squared is 9, add those together, I get the square root of 10 for side AB. Stay organized up here. Side AB, square root of 10. Okay, helpful hint for you just so that this video is not going to go on forever. When you do side CD, you would also get the square root of 10. Okay, so using the points C and D, when you plug them into the distance formula, you get the same value, the square root of 10. Okay, you must show proof of this though on test day. You'll have to do the distance formula for that side as well. Right, looking at side BC, we're going to do those next. Staying organized, writing BC, point B is located at -1, +5. Point C is located at +6, +1. We're going to label our points, plug them in. X1, Y1, X2, Y2, going into my distance formula. X2 minus X1, 6 minus -1 gets squared, plus Y2 minus Y1, that's 1 minus 5 squared. Parentheses first, 6 minus -1 is +7, 1 minus 5 is -4. Now we're doing exponents, 7 squared is +49, -4 squared is +16. Those combine to give me the square root of 65 for segment BC. And again, just for the sake of time in recording this video, when you use A and D for side AD, you would also get the square root of 65 units. Right, just make sure that you are doing that work on the test day. So AD in the distance formula would also yield the square root of 65. From there, I can calculate my perimeter by adding these all together. Now, this doesn't work the way you might assume. That square root of 10 plus the square root of 10 plus the square root of 65 plus the square root of 65. Like if you add all those numbers together, you get 150. But the square root of 150 is not the answer to the perimeter of this. We would have to square root each individual term and then add those together. So our square root of 10s are about 3.2. Our square root of 65 is about 8.1. And so now those values can all be added together to get our perimeter. So 3.2 plus 3.2 plus 8.1 plus 8.1 will give us about 22.6 for our perimeter on this figure. Now finding the area on this figure would require the box method that we learned. So I can't use an area formula with these things that are not countable by finger. So I'm gonna use the box method instead. Remember, that starts with us drawing a box that's exactly as wide and as tall as our figure is on the graph. So that box would look like this, roughly. And the first thing we would do would be to find the area of that box. So I'm gonna stay organized. The area of this would be found by doing base times height. For this specific box, if I count, I got 1, 2, 3, 4, 5, 6, 7, 8 on the bottom. I have 1, 2, 3, 4, 5, 6, 7 on the side. My area would be found by doing base of 8 times the height of 7, and I get 56 units squared for that box. From there, we're finding the area of the surrounding triangles. So I have this triangle in the top left, just triangle 1, triangle 2 here, triangle 3 in the bottom right, triangle 4 up here in the top right. And I'm trying to find the area of all these triangles, right? So triangles, remember, is base times height divided by 2. The reason this method helps us here is because for all those triangles, I can count the base and height, because these are all right triangles. So that means those legs, those countable sides, can be my base and my height. So for triangle 1, I can say a base of 1 and a height of 3 here. That's 1, this is 3. So base is 1, height is 3, and I can plug these into my area formula for the triangle. Base times height divided by 2. 3 divided by 2 gives me 1.5 units squared for that triangle. And then I'm just going to do that for all 4 of my triangles. For triangle 2, if I count my base, I'm going to get 7. My height would be 4, and I can plug those in. So again, that's right here. That's 7. This is 4. So base is 7, height of 4. Plugging those in. 7 times 4 divided by 2. 7 times 4 is 28. 28 divided by 2 gives me 14 units. Pen's not working. Units squared, okay? Just to save time in the video, when I calculate base and height for triangle 3, I would also get 1.5 units squared, the same as that little triangle up here. When I do it for triangle 4, I will also get 14 units squared. It's the same dimensions as this, right? 7 and 4. So again, now I can find the area of my original shape here by getting the area of that box, that 56 units squared, and just taking away those 4 triangles. So subtracting those values. So in the end, I'm doing the box minus the triangles, right? So 56 from my box minus the 1.5s from the small triangles minus the 14s from the bigger triangles will get me to my final answer here. So I'll need to calculate really quick. Minus 1.5 minus 1.5 minus 14 gives us 25 units squared for the area of that quadrilateral. Guys, that's our study guide. If you know how to do all of these problems, you're going to be in great shape for the test. I should say, if you're confident that you can do all these problems again without looking at notes, without watching a video, then you're in great shape for our summit. All right, happy studying. I'll see you in the next one. Bye, guys.